Hello, I welcome you all in this presentation related with the subject fundamentals of surface engineering. And we are talking about the techniques for the surface modification, especially use of the development of layer of the suitable materials so that the required improvement in surface properties can be achieved for longer tribological life of the component. So, under this approach, we have talked about the various surface modification techniques, especially related with the weld surfacing techniques like the weld surfacing using gas welding, shielded metal arc welding, submerged arc welding processes, and the gas metal and the flux core arc welding process also. In this presentation specifically we will be talking about the two processes, and these are like gas tungsten arc welding and plasma arc welding. In all the welding related processes where a layer of the metal is deposited onto the surface of the substrate for surface modification, a bead on plate or bead on the substrate is deposited, and the different processes work on the different approaches associated with the protection of weld pool which is formed while depositing the bead on plate weld, and they also differ with regard to the energy density associated with each of the process, associated with each of welding process, and these two factors in turn affects the quality of the weld deposit which is produced. So, as far as these two processes are concerned, first of all we will talk about the gas tungsten arc welding, which in short is termed as GTAW process. In this process we use one non-consumable tungsten electrode which is invariably connected to the negative terminal of the power source. This is power source, and we invariably use the DC. However, while depositing the non-ferrous metals we can use AC as well. So, the positive terminal is connected to the workpiece. This is the normal configuration related with the power source connection is used, and after striking the arc either using the high frequency unit, the arc is established, or by touch method where electrode is brought in contact with the substrate and then it is moved apart after use of the proper power setting like the 12 to 15 open circuit voltage is normally used, and the current we can choose as per our requirement, the kind of the heat that we want to generate. And once the arc is established, the heat is used for fusion of the substrate, thin layer of the substrate, very thin layer of the substrate is brought to the molten state, and since the electrode is non-consumable and made of the tungsten, so to deposit the material for surface modification we have to feed it from outside. So, the electrode or filler wire is fed into the arc zone, so that after melting it gets deposited over the surface of it gets mixed with the molten substrate material and forms a layer of the modified composition in form of the bead on plate weld. Since the electrode is non-consumable and the filler wire is fed in the arc zone, which is at quite a high temperature like 5000 to 10,000 degrees centigrade. The temperature is usually higher than what is normally observed in case of like shielded metal arc welding or the gas metal arc welding processes. So, the high temperature and the enough heat generation through the VI facilitates the melting of the filler wire, and the melting of the filler wire, which is the material to be deposited in form of the bead on plate weld onto the substrate for surface modification. And this material can be selected as per our requirement. It may be ASS for corrosion resistance, or it may be nickel tungsten carbide kind of the material for surface modification as per our need. So, idea here is that filler metal is melted and mixed with the molten substrate, so that substrate surface layers, so that required surface modification can be achieved. There are few good points as far as this process is concerned, since this process works with very low current and low voltage levels, and therefore the heat input associated with the process, which is specifically written as a net heat input, is very low. So, this process is known as low heat input process. And another aspect is that the distance between the electrode and the substrate is also very less. So arc gap is small. The length or standoff distance between the electrode and the workpiece is very less, and that is why chances for entry of the atmospheric gases in the arc zone is less, and through the use of the inert gases we provide the required shielding. So, there are few good points, that very small arc gap and the use of the argon or helium as a shielding gas. These provide very effective protection to the molten metal which is being formed during the weld bead deposition by the GTAW process. So, this one is protected very effectively. And another aspect, as I have said, the process is low net heat input because of use of the very low current and the low voltage, and this magnitude may be very likely 0.1 to 1 joule kilojoule per mm. This is the kind of heat input which is very less. So, the low heat input associated with this process helps in reducing the thermal damage to the substrate due to the weld thermal cycle, as well as it also reduces the thermal damage to the surfacing material, weld surfacing material, which is being applied for the weld surface modification. So, the two aspects, very good protection, helps to avoid the interaction of the molten metal with the atmospheric gases, which reduces the possibility for inclusions, and the less heat input associated with this process reduces the thermal damage associated with the weld surfacing, and both these factors helps in improving the quality of the weld deposits. More specifically, if we see the reduced heat input, reduced H net increases the cooling rate during the solidification. So, solidification time is reduced, and which in turn helps in refinement of the grain structure of the weld deposits which are made, and this kind of the refinement, so improved quality in terms of the absence of the inclusions and the very refined grain structure, very less thermal damage, reduced thermal damage in terms of the adverse effect with regard to the residual stresses or cracking tendency or the wider heat effector zone formation. So, all those adverse effects onto the substrate and the weld surfacing materials are reduced when the heat input is reduced, and that is why GTAW process offers the better quality of the weld deposits as compared to the SMAW and submerged arc welding processes. However, there are some negative points associated with this process, that is, since the process uses the non consumable tungsten electrode, which is primarily used for the striking of the arc, so that heat can be generated, and that heat is eventually used for surface modification by melting the layer of surface substrate material as well as the filler material. So, the filler metal is added externally, means it is to be added from outside. So, one separate mechanism is needed to feed the electrode in the arc zone, and this reduces the rate of deposition of the metal during the weld surfacing. So, the productivity associated with this process is very low, because the amount of the metal which can be deposited for surface modification using this process is very less. It may be like 2 to 3 kg per hour. So, this is the negative effect. However, the quality, this is very negative side related with the GTAW process for the weld surfacing. However, the quality of the weld deposits or the weld surfacing produced by the GTAW process is very good, and therefore to overcome this aspect, another variant of the GTAW process has been developed, which is called hot wire GTAW process. As I have said, in the conventional GTAW process, heat input is very low, energy density is higher than the SMAW and SAW process, and these two factors in turn help in reducing the dilution level. That is, the quality of the material which is being deposited is degraded to lesser extent due to the limited melting of the substrate and getting it mixed with the filler metal which is being deposited. So, the reduced dilution associated to the GTAW process is another positive side, but we need to overcome the low melting due to the low deposition rate issue related with the GTAW process. So, what we do basically, we use the conventional GTAW power source like this, where negative terminal is connected to the electrode and positive terminal is connected to the substrate. Arc is established. So, this will be facilitating the melting of the substrate up to some depth. Then we use whatever filler is being fed in the arc zone for developing the bead-on plate weld surfacing. This filler is preheated. This is so preheating of filler wire using electrical resistance heating with the help of alternating current. So, the filler wire is fed with the AC current in between before feeding it into the arc zone. So, this will be helping to preheat the filler wire with the use of AC for with the use of AC. AC will be causing the electrical resistance heating of the filler wire. So, once the preheated filler wire is fed in the arc zone, it requires less heat for fusion to take place, and that in turn facilitates the faster melting of the filler wire when it is fed in the arc zone. So, the net advantage is what? It requires less heat from arc for fusion of the filler wire due to the preheating, and reduced need of the heat facilitates the faster melting of the filler wire. So, faster melting of the filler, these two factors in turn increase the deposition rate of the filler which is being applied onto the surface of the substrate. So, as I have said, like 2 to 3 kg per hour filler metal if deposited using the conventional GTAW process, then hot wire GTAW process can increase this 8 to 10 kg filler metal deposition per hour. So, this significant increase in the deposition rate associated with the hot wire GTAW process is facilitated primarily due to the preheating of the filler wire before feeding it into the arc zone for fusion to take place, and this happens primarily due to the preheat facilitated by the electrical resistance heating approach use of the AC. Normally we use the DC current for the GTAW process, but for preheating of the electrode we use AC in order to avoid any the arc blow related issue during the weld surfacing, because if we use the DC current for preheating of the filler wire, then the electromagnetic fields associated with the DC current being fed in the filler wire and DC current being used for developing the arc, these two electromagnetic fields can interact with each other and can cause the problem of the arc blow, which will primarily be involving the deflection of the arc from its intended path or intended location, and that will be leading to the deposition of the filler metal at the location elsewhere as compared to the location where we want. So, this will be leading to the primarily misplacement of the molten metal or the weld bead which is being deposited, and if the weld bead is deposited at the location where we do not want, that's it, then it will simply be leading to the wastage of the resources. So, to avoid such kind of the tendency related to the arc blow, the DC is used primarily for developing the arc and AC is used for preheating of the filler wire. Now, we will be talking about the another process process of the weld surfacing, and that is called plasma arc welding. So, the plasma arc welding is we can say as an enhanced or advanced version of the GTAW process, gas tungsten arc welding process, because in plasma also we use one tungsten electrode and arc is established between the workpiece and between the electrode which is made of tungsten and the substrate, and the power supply negative terminal is connected to the electrode and the positive terminal of the power source is connected to the substrate. But in this process whatever arc is generated, arc is primarily used to generate the plasma, and plasma is forced to pass through the nozzle. So, basically here we have one electrode, there is one nozzle. So, initially arc is established between the nozzle and the electrode, and the plasma forming gas is fed. So, the plasma forming gas will be passed through the arc, and this plasma then will be passed through the nozzle. So, this nozzle basically will be converging, or more technically it is termed as constricting the arc. So, the arc is there initially between the electrode and the nozzle, and the plasma forming gas is passed through the arc, which will be leading to the formation of the plasma. Plasma is forced to pass through the nozzle of the smaller diameter, that will be causing the constriction of the arc, and then this plasma will be impacting with the surface of the substrate. So this is how the plasma will be leading to the transfer of the heat from the arc zone to the substrate. Now as per the case, there are two variants which are used in the plasma welding. One is called non transferred plasma and another is transferred plasma. In case when the workpiece is independent of the power source, like this, electrode is connected to the negative terminal and the positive terminal is connected to the nozzle, arc is established and then plasma forming gas is passed, and thereafter plasma is forced to pass through the nozzle, that then plasma will be impinging with the surface of the substrate. This is the case when there is workpiece is not the part of the electric circuit. This one is called non transferred plasma. In this case the arc is independent of the workpiece, only the plasma whatever is coming out of the nozzle will be impinging with the surface of the substrate. In another case, electrode is the very much part of the workpiece is very much workpiece of the substrate is very much part of the electric circuit. In this case the arc is striked between the electrode and the workpiece, and the workpiece is very much part of the electric circuit. Here it is connected to the positive terminal and the negative terminal is connected to the electrode, and the plasma forming gas is passed through, and then whatever plasma is formed, that will be passed through the nozzle. So in this case the plasma whatever plasma is formed, that will be passed through the constricting nozzle. So idea here is to reduce the diameter, or you can say the cross section of the plasma arc which is being formed. This in turn will be increasing the energy density, and increase in energy density will be reducing the heat input required for fusion of the substrate as well as filler metal, and the reduced heat input in turn will be increasing the cooling rate during the solidification. Increase in cooling rate will be reducing the grain size. So this is the kind of the technical chain of the reactions which is formed. Due to the constriction of the plasma, in case of the plasma arc welding, we get the higher energy density due to the reduced cross section of the plasma. Higher energy density reduces the heat input required for weld surfacing. Reduced heat input helps in higher cooling rate, and this will be refining the grain structure. Apart from the reduction in the heat input due to the increase in energy density associated to the plasma arc, this will also be reducing the dilution level, and this will also be reducing the thermal damages associated with the weld thermal cycle. Since the plasma arc has all the benefits of the GTAW, additionally it offers the advantage of the higher energy density, and therefore we find the higher deposition rate and the good quality, the weld surfacing, and a much higher temperature of the plasma zone. And because of this we are able to develop the weld surfacings of the high temperature materials also. And as a typical example, this is used for development of the cobalt base alloy weld surfacing, where in PTAW, this is called plasma transferred arc welding. So, in case of the plasma transferred arc welding, the electrode and workpiece. So, the arc is there between the electrode and the workpiece, and the plasma forming gas will be passed through, it will be passing through the nozzle, and then it will be impinging with the surface of the substrate. So, filler wire has to be fed, like in GTAW process, filler wire has to be fed in the plasma zone, so that melting can be facilitated. Since the energy density is very high, higher than the GTAW process, so it offers the advantage of the reduced heat input while facilitating the melting of the high temperature materials also. This in turn reduces the dilution, increases the cooling rate, reduces the thermal damage associated with the thermal damage due to the weld thermal cycle associated with the PTAW process, and such kind of the claddings are found to be very sound, good, leading to the good metallurgical bonding and free from the defects like inclusions, no inclusions, and these factors in turn help in developing the good quality weld surfacings. So, the plasma arc or PTAW process, plasma transferred arc welding, is very effectively used as a mass process for developing the large scale weld surfacing for improving the wear resistance of the number of the tribological components, especially by developing the wear resistant materials like cobalt based alloys, stellites, etc. And we notice that these are very effectively used for developing the weld surfacings in the field of hydro power plants, for increasing the cavitation resistance, for increasing the abrasion resistance in the mining industry, and in the construction industry where good abrasion resistance is required. So, now I will summarize this presentation. In this presentation, basically I have talked about the gas tungsten arc welding and the plasma arc welding processes, and we have seen that both these processes use the non-consumable tungsten electrode for developing the arc, which and the heat of the arc is used for fusion of the filler metal, so that the required surface modification of the substrate can be realized. Thank you for your attention.